In the next 3 segments, we will change gears a little bit and talk about the definition of a PRG. This definition is a really good way to think of a PRG, and we will see many applications for this definition. So consider a PRG with key space k that outputs n-bit strings. Our goal is to define what does it mean for the output of the generator to be indistinguishable from random. In other words, we're going to define a distribution that basically is defined by choosing a random key in the key space. Remember that arrow with R above it means choosing uniformly from the set script k, and then we output basically the output of the generator. And what we'd like to say is that this distribution of pseudo-random strings, is indistinguishable from a truly uniform distribution. In other words, if we just choose a truly uniform string in 0, 1 to the n, and simply output this string, we'd like to say that these two distributions are indistinguishable from one another. Now, if you think about it, this sounds really surprising, because if we draw a circle here of all possible strings in 0, 1 to the n, then the uniform distribution basically can output any of these strings with equal probability. That's the definition of the uniform distribution. However, a pseudo-random distribution generated by this generator G, because the seed space is so small, the set of possible outputs is really, really small. It's tiny inside of 0, 1 to the n, and this is really all that the generator can output. And yet what we're arguing is that an adversary who looks at the output of the generator in this tiny set can't distinguish it from the output of the uniform distribution over the entire set. Okay? That's the property that we're actually shooting for. So to understand how to define this concept of indistinguishability from random, we need the concept of a statistical test. So let me define what a statistical test on 0, 1 to the n is. I'm going to define these statistical tests by the letter A. And a statistical test is basically an algorithm that takes as input an n-bit string and simply outputs 0 or 1. Now I'll tell you that 0, we're going to think of it as though the statistical test said, the input you gave me is not random. And 1, we're going to think of it as saying that the input you gave me actually is random. Okay, so all the statistical test does is it basically takes the input x that was given to it, the n-bit string that was given to it, and decides whether it looks random or it doesn't look random. Let's look at a couple of examples. So the first example basically will use the fact that for a random string, the number of zeros is roughly equal to the number of ones in that string. In other words, the statistical test is going to say 1 if and only if basically the number of zeros in the given string x minus the number of ones in the given string x is these two numbers are not too far apart. In other words, the difference between the number of zeros and the number of ones, let's just say, is less than 10 times square root of n. Okay, so if the difference is less than 10 times square root of n, the statistical test will say, hey, the string x looks random. If the difference happens to be much bigger than 10 times square root of n, that starts to look suspicious, and then the statistical test will say, hey, the string you gave me does not look random. Okay, so this is our first example of a statistical test. Let's look at another similar example. We'll say here, the statistical test will say 1 if and only if, say, the number of times that we have 2 consecutive zeros inside of x. Well, let's think about this for a second. This basically, again, counts in this string of n bits, it counts the number of times that we see the pattern 0, 0, 2 consecutive zeros. Well, for a random string, we will expect to see 0, 0 with probability 1/4, and therefore in a random string, we'll expect about n over 4 0 zeros. Yeah, n over 4 blocks of 0, 0. And so what the statistical test will do is it will say, well, if the number of 0 zeros is roughly n over 4, in other words, the difference between the number and n over 4 is, say, less than 10 square root of n, then we will say that x looks random. And if the gap is much bigger than n over 4, we'll say, hey, this string doesn't really look random, and then the statistical test will output 0. Okay, so here are 2 examples of statistical tests that basically, for random strings, they will output 1 with very high probability. But for strings that, don't look random, for example, think of the all 0 string. For the all 0 string, neither one of these tests will output 1. And in fact, the all 0 string does not look random. Let's look at one more example of a statistical test, just to kind of show you that basically statistical tests can pretty much do whatever they want. So here's a third example. Let's say that the statistical test outputs 1 if and only if, say, the biggest block, so we'll call this the maximum run of 0 inside of the string x. This is basically the longest sequence of zeros inside of the string x. In a random string, you expect the longest sequence of zeros to be roughly of length log n. So we'll say if the longest sequence of 0 happens to be less than 10 times log n, then this test will say that x was random. But if all of a sudden we see a run of zeros that say is much bigger than 10 log n, then the statistical test will say the string is not random. Okay, so this is another crazy thing that the statistical test will do. By the way, you notice that if you give this test the all 1 string, so 1, 1, 1, 1, 1, this test will also output 1. In other words, this test will think that the all 1 string is random, even though it's not. Yeah, even though the all 1 string is not particularly random. Okay, so statistical tests don't have to get things right. They can do whatever they like. They can test, they can decide to output random or not, 0 or 1, however they like. And similarly, there are many other statistical tests. There are literally hundreds of statistical tests that one can think of. And I can tell you that in the old days, basically the way you would define that something looks random is you would say, hey, here's a battery of statistical tests, and all of them said that the string looks random. Therefore, we say that this generator that generated the string is a good generator. In other words, this definition that uses a fixed set of statistical tests is actually not a good definition for security, or more generally for crypto. But before we talk about actually defining security, the next thing we talk about is how do we evaluate whether a statistical test is good or not. So to do that, we define the concept of advantage. And so let me define the advantage. So here we have a generator that outputs n-bit strings, and we have a statistical test on n-bit strings. And we define the advantage of this generator. I'll denote it by advantage sub PRG. The advantage of the statistical test A relative to the generator G, I'll define it as follows. It's basically the difference between two quantities. The first quantity is basically we ask how likely is the statistical test to output 1 when we give it a pseudo-random string. Okay, so here k is chosen uniformly from the seed space. And we ask how likely is the statistical test to output 1 when we give it a pseudo-random output generated by the generator. Versus, now we ask how likely is the statistical test to output 1 when we give it a truly random string. So here r is truly random in 0, 1 to the n. Okay? And yeah, we look at the difference between these two quantities. Now you realize because these are differences of probabilities, this advantage is always going to lie in the interval 0, 1. So let's think a little bit about what this advantage actually means. So first of all, if the advantage happens to be close to 1, well, what does that mean? That means that somehow the statistical test A behaved differently when we gave it pseudo-random inputs, when we gave it the output of the generator, from when we gave it truly random inputs, right? It somehow behaved differently. In one case, it output 1 with a certain probability, and in the other case, it output 1 with a very different probability. Okay, so somehow it was able to behave differently, and what that really means is that the statistical test can basically distinguish the output of the generator from random. Okay, so in some sense we'll say that the statistical test broke the generator G because it was able to distinguish the output from random. However, if the advantage is close to 0, well, what does that mean? That means that basically the statistical test behaves pretty much the same on pseudo-random inputs as it does on truly random inputs. And basically there we would say that A could not distinguish the generator from random. Okay, so this gives you a little bit of intuition about why this concept of advantage is important. It basically tells us whether A was able to break the generator, namely distinguish it from random, or not able to break it. So let's look first of all at a very silly example. Suppose we have a statistical test A that simply ignores its inputs and always outputs 0. Okay, always outputs 0. What do you think is the advantage of the statistical test relative to a generator G? So I hope everybody said the advantage is 0. Let me just explain why that's the case. Well, if the statistical test always outputs 0, that means that when we give it pseudo-random input, it will never output 1. So the probability that it outputs 1 is 0. Similarly, when we give it truly random input, it still will never output 1. And so the probability that it outputs 1 is 0. And so 0 minus 0 is 0. so its advantage is 0. So basically, a statistical test that ignores its input is not able to distinguish truly random input from a pseudo-random input, obviously. Okay, so now let's look at a more interesting example. So suppose we have a generator G that satisfies a funny property. It so happens that for 2/3 of the keys, the first bit of the output of the generator happens to be 1. Okay, so if I choose a random key with probability 2/3, the generator will output 1 as its first bit. Okay, so that's the property of the generator that we're looking at. Now let's look at the following statistical test. The statistical test basically says, if the most significant bit of the string you gave me is 1, I'm going to say 1, meaning I think it's random. If the most significant bit of the string you gave me is not 1, well, namely 0, I'm going to say 0. Okay, so now my question to you is, what is the advantage of this statistical test on the generator G? Okay, so remember I just wrote down the definition here again, and I'll let you think about this for a second. So let me explain. Suppose we give the statistical test pseudo-random input. By definition of G, we know that with probability 2/3, the first bit in the input will start with the bit 1. But if it starts with the bit 1, then the statistical test will output 1. In other words, the probability that the statistical test outputs 1 is exactly 2/3. Now let's look at the case of a random string. If I give you a random string, how likely is it that the most significant bit of the random string is 1? Well, for a random string, that happens exactly half the time. And so in this case, the statistical test will output 1 with probability 1/2. And so the overall advantage is 1/6, and 1/6 is actually a non-negligible number. That's actually a fairly large number, which basically means that this A was able to distinguish the output. We'll say that A breaks the generator G with advantage 1/6. Okay, which basically means that this generator is no good, is broken. Okay, so now that we understand what statistical tests are, we can go ahead and define what is a secure pseudo-random generator. So basically we say that a generator G is secure if essentially no efficient statistical test can distinguish its output from random. More precisely, what we'll say is that basically for all efficient statistical tests A, it so happens that if I look at the advantage of the statistical test A relative to G, this advantage basically is negligible. Okay, so in other words, it's very close to 0, and as a result, this statistical test was not able to distinguish the output from random, and that has to be true for all statistical tests. So this is a very, very pretty and elegant definition that says that a generator is secure not only if a particular battery of statistical tests says that the output looks random, but in fact all efficient statistical tests will say the output looks random. Okay? One thing I'd like to point out is that the restriction to efficient statistical tests is actually necessary. If we ask that all statistical tests, regardless of whether they're efficient or not be able to distinguish the output from random, then in fact that cannot be satisfied. So in other words, if we took out the requirements that the test be efficient, then this definition would be unsatisfiable, and I'll leave this as a simple puzzle for you to think about. But basically the fact is that restricting this definition to only efficient statistical tests is actually necessary for this to be satisfiable. Now that we have a definition, the next question is, can we actually construct a generator and then prove that in fact it is a secure PRG? In other words, prove that no efficient statistical test can distinguish its output from random. And it turns out that the answer is we actually can't. In fact, it's not known if there are any provably secure PRGs, and I'll just say very briefly, the reason is that if you could prove that a particular generator is secure, that would actually imply that P is not equal to NP. And I don't want to dwell on this because I don't want to assume you guys know what P and NP are, but I'll just tell you as a simple fact that in fact if P is equal to NP, then it's very easy to show that there are no secure PRGs. And so if you could prove to me that a particular PRG is secure, that would imply that P is not equal to NP. Again, I will leave this to you as a simple puzzle to think about. But even though we can't actually rigorously prove that a particular PRG is secure, we still have lots and lots and lots of heuristic candidates, and we even saw some of those in the previous segment. Okay, now that we understand what is a secure PRG, I want to talk a little bit about some applications and implications of this definition. And so the first thing I want to show you is that in fact a secure PRG is necessarily unpredictable. In a previous segment we talked about what it means for a generator to be unpredictable, and we said that basically what that means is that given a prefix of the output of the generator, it's impossible to predict the next bit of the output. Okay, so we'd like to show that if a generator is secure, then necessarily it means it's unpredictable. And so the way we're going to do that is using the contrapositive. That is, we're going to say that if you give me a generator that is predictable, then necessarily it's insecure. In other words, necessarily I can distinguish it from random. And so let's see, this is actually a very simple fact, and so let's see how we would do that. So suppose you give me a predictor. In other words, suppose you give me an efficient algorithm such that, in fact, if I give this algorithm the output of the generator, but I give it only the first I bits of the output, it's able to predict the next bit of the output. In other words, given the first I bits, it's able to predict the I plus first bit, and it does that with a certain probability. So let's say if we choose a random k from the key space, then clearly a dumb predictor would be able to predict the next bit with probability 1/2, simply just guess a bit. You'll be right with probability 1/2. However, this algorithm A is able to predict the next bit with probability 1/2 plus epsilon. So it's bounded away from 1/2, and in fact we require that this be true for some non-negligible epsilon. So for example, epsilon equals 1/1000 would already be a dangerous predictor because it can predict the next bit given a prefix with non-negligible advantage. Okay, so suppose we have such an algorithm. Let's see that we can use this algorithm to break our generator. In other words, to show that the generator is distinguishable from random and therefore is insecure. So what we'll do is we'll define a statistical test. So let's define a statistical test B as follows. Basically, B given a string x, what it will do is it will simply run algorithm A on the first I bits of the string x that it was given, and statistical test B is simply going to ask, was A successful in predicting the I plus first bit of the string? If it was successful, then it's going to output 1, and if it wasn't successful, then it's going to output 0. Okay, this is our statistical test. Let's put it in a box so we can take it wherever we like, and we can run the statistical test on any n-bit string that's given to us as input. So now let's look at what happens. Suppose we give the statistical test a truly random string, so a truly random string R, and we ask what is the probability that this statistical test outputs 1? Well, for a truly random string, the I plus first bit is totally independent of the first I bits. So whatever this algorithm A is going to output is completely independent of what the I plus first bit of the string R is. And so whatever A outputs, the probability that it's going to be equal to some random bit xi plus 1, random independent bit xi plus 1, that probability is exactly 1/2. In other words, algorithm A simply has no information about what the bit xi plus 1 is, and so necessarily the probability that it's able to predict xi plus 1 is exactly 1/2. On the other hand, let's look at what happens when we give our statistical tests a pseudo-random sequence. Okay, so now we're going to run the statistical test on the output of the generator, and we ask how likely is it to output 1? Well, by definition of A, we know that when we give it the first I bits of the output of the generator, it's able to predict the next bit with probability 1/2 plus epsilon. So in this case, our statistical test B will output 1 with probability greater than 1/2 plus epsilon. And basically what this means is if we look at the advantage of our statistical tests over the generator G, it's basically the difference between this quantity and that quantity. And the difference between the two, you can see, is clearly greater than an epsilon. So what this means is that if algorithm A is able to predict the next bit with advantage epsilon, then algorithm B is able to distinguish the output of the generator with advantage epsilon. Okay, so if A is a good predictor, B is a good statistical test that breaks the generator. And as we said, the contrapositive of that is that if G is a secure generator, then there are no good statistical tests, and as a result, there are no predictors. Okay, and which means that the generator is, as we said, unpredictable. Okay, so far what we've seen is that if the generator is secure, necessarily it's impossible to predict the I plus first bit given the first I bits. Now, there's a very elegant and remarkable theorem due to Yao back in 1982 that shows that in fact the converse is also true. In other words, if I give you a generator that's unpredictable, so you cannot predict the I plus first bit from the first I bits, and that's true for all I, that generator in fact is secure. Okay, so let me state the theorem a little bit more precisely. So here we have our generator that outputs n-bit outputs. The theorem says the following: basically for all bit positions, it's impossible to predict I plus first bit of the output given the first I bits, and that's true for all I. In other words, again, the generator is unpredictable for all bit positions. Then that in fact implies that the generator is a secure PRG. I want to paraphrase this in English, and so the way to kind of interpret this result is to say that if basically these next bit predictors, these predictors that try to predict the I plus first bit given the first I bits, if they're not able to distinguish G from random, then in fact no statistical test can distinguish G from random. So kind of next bit predictors are in some sense universal predictors when it comes to distinguishing things from random. This theorem, by the way, it's not too difficult to prove, but there's a very elegant idea behind its proof. I'm not going to do the proof here, but I encourage you to think about this as a puzzle and try to kind of prove this theorem yourself. Let me show you kind of one cute implication of this theorem. So let me ask you the following question. Suppose I give you a generator, and I tell you that given the last bit of the output, it's easy to predict the first bit of the outputs. Okay, so given the last n bits, you can compute the first n bits. That's kind of the opposite of predictability, right? Predictability meant given the first bits, you can produce the next bits. Here, given the last bits, you can produce the first ones. And my question to you, does that mean that the generator is predictable? Can you somehow, from this fact, still build a predictor for this generator? So this is kind of a simple application of Yao's theorem, and let me explain to you. The answer is actually yes, and let me explain why. How do we build this generator? Well, actually, we're not going to build it. I'm just going to show you that the generator exists. Well, because the last n over 2 bits imply the first n over 2 bits, that necessarily means that the generator, here, let me write it this way, that necessarily means that G is not secure. Because just as we did before, it's very easy to build a statistical test that will distinguish the output of G from uniform. So G is not secure. But if G is not secure, by Yao's theorem, that means that G is predictable. So in other words, there exists some I for which, given the first I bits of the output, you can build the I plus first bit of the output. Okay? And so even though I can't quite point to you to a predictor, we know that a predictor must exist. So that's one cute, simple application of Yao's theorem. Now, before we end this segment, I want to kind of generalize a little bit what we did and introduce a little bit of important notation that's going to be useful actually throughout. So we're going to generalize the concept of indistinguishability from uniform to indistinguishability of two general distributions. So suppose I give you P1 and P2, and we ask, can these two distributions be distinguished? And so we'll say that the distributions are computationally indistinguishable, and we'll denote this by P1 is squiggly P, P2. This means that in polynomial time, P1 cannot be distinguished from P2, and we'll say that they're indistinguishable basically just as before, if basically for all efficient statistical tests A, it so happens that if I sample from the distribution P1 and I give the output to A, versus if I sample from the distribution P2 and I give the sample to A, then basically A behaves the same in both cases. In other words, the difference between these two probabilities is negligible. And this has to be true for all statistical tests, for all efficient statistical tests. Okay, so if this is the case, then we say that, well, A couldn't distinguish, its advantage in distinguishing two distributions is negligible, and if that's true for all efficient statistical tests, then we say that the two distributions are basically computationally indistinguishable, because an efficient algorithm cannot distinguish them. And just to show you how useful this notation is, basically using this notation, the definition of security for a PRG just says that if I give you a pseudo-random distribution, in other words, I choose K at random and then output G of K, that distribution is computationally indistinguishable from the uniform distribution. So you can see this very simple notation captures the whole definition of pseudo-random generators. Okay, so we're going to make use of this notation in the next segment, when we define what does it mean for a cipher to be secure.